Hello, my name is Vargas.
I'm Wechsler.
Camilo, Torres.
And I'm Rafael, Diaz.
And we're working on the upright landing payload for the NASA student launch. So the purpose of this project is, the competition is to be able to design and manufacture a rocket that reaches an apogee of 5,280 feet and have a payload that is able to descend, have a stabilized descent and have an upright landing. Our senior design objectives for the payload is to be able to stabilize this descent and so it lands upright. The problems faced in this project are problems that are also faced in the aerospace, have been faced in the aerospace industry. The in-flight stability is required for some sensors. Upright landing is required for some payloads such as extraplanetary vehicles and transporting human beings. And upright landing can be cost-effective. This allows us to recover and reuse expensive equipment.
Okay, for landing the payload upright, we chose to go with a multicopter. Here we have some of the issues that may have, some of the benefits and the negative things that we have from increasing the motors. We have an increase of thrust and increased stability as we increase the number of motors, but also we have more power requirements and increased weight. Here we have some of the different types of multicopters. We have the tricopter, which is a 3-motor configuration, the quadcopter X and H configuration, which are 4 motors. We have the Y4 and Y6, which are coaxial motor configurations, the hexacopter, which are 6 motors. And then for our final design, we decided to go between the quadcopter and hexacopter. The hexacopter has the capability of operating if there was some failure in one of the motors, and the quadcopter, due to its stability nonetheless and less cost, we picked to go to the quadcopter.
When it comes to the propellers that we're going to be utilizing for our quadcopter, there are 2 factors we have to consider, the length and the pitch. If we increase the length, that does result in an increase in efficiency. However, it also results in increased current draw and a decrease in the ability of the quadcopter to change its speed. With regard to increasing pitch, if we increase the pitch, we do get increased thrust. However, we also get an increased current draw, and there's also a decrease in stability, and that's due to the increased volume of air flowing through the propeller, causing more air turbulence. The decrease in stability is of primary concern to us because we need to ensure that the onboard camera is capable of detecting targets on the ground. So we're going to be utilizing propellers with low pitch, and as far as length goes, we're going to take recommendations from the manufacturer of the motors. Speaking of the motors, we are going to be utilizing thrust data tables. Thrust data tables are often provided by motor manufacturers, and what they do is they report the expected amount of thrust from a motor given the amount of voltage supplied, as well as the pitch and length of the propeller. So we'll be using this as a guide and then doing our own testing with a variety of propellers. Now, the typical thrust-weight ratio when we're talking about how much thrust we need is 1.5 for multicopters that are used for videography or photography. However, our payload never needs to ascend. It is strictly descending. So a thrust-weight ratio of 1.5 is more than we need. We then did a force analysis, and the forces acting on the quadcopter are the thrust from the motors, the weight, also the force from drag from a parachute that will be utilized in the quadcopter, and the force from drag from the quadcopter itself. When we analyzed this, we were able to determine that our expected terminal velocity is about 21 feet per second. We then rewrote that formula in terms of the velocity as a function of time, and we got this differential equation. When that was solved, this allowed us to experiment with a few different possible thrusts. And as an example, with our expected weight of 3.7 pounds on the quadcopter, with a thrust of just 4 pounds, which is about a thrust-weight ratio of about 1.1, we can get from terminal velocity to a velocity of 0 within 4 seconds at about 33 feet. Now, stability is going to be achieved through the use of a PID controller, which is software that is part of the flight controller. What it does is it receives input from various sensors, such as an accelerometer and gyroscope, and then sends instructions to the motors in order to achieve stability. There are 3, the PID stands for proportional, integral, and derivative. And those are 3 types of errors that can occur. And so what we need to do as part of our calibration process is determine how much we need to weight each one of those errors in order to achieve stability without suffering from oscillation. Here are some of our alternative designs. The first one on the left is a rather interesting coaxial bicopter. The advantage is that the arms of the propellers are not needed. Those do not need to extend. It is unusual. The downside is that the RGU Pilot open source software that we're going to be editing for our purposes comes with a variety of code for a variety of multicopters. However, the coaxial bicopter is not one of them. That means that we would have to program the flight controller from scratch, which is an inordinate amount of work. In the center there, we have just an alternative design for extending the arms of the propellers. We call this a spiral design. This has some drawbacks in that it really limited the length of the propellers. It also limited the distance the propellers were from the center of gravity, which in turn reduces the amount of moment that the propellers generate, and that's very important when you're trying to achieve stability. This last design alternative we have here is a little bit closer to our final design. As you can see, the arms rotate upwards and then the propellers extend linearly outwards. The legs also descend linearly outwards, and then through the use of spring hinges, unfold through rotational motion as well. And we determined, or we decided that having to have both linear and rotational motion was more complicated than it needed to be, and that we could achieve our desired result with just rotational motion. So here's our proposed design. You can see the 2 yellow circles on top are the NASA mandated parachute and redundant parachute. And on the left, you see it in its stored position after it is ejected from the rocket and eventually reaches this extended configuration with both the arms and legs extended.
Okay, so there are several design considerations, time constraints that must be taken into account when narrowing down our final design. So when the quadcopter is being ejected from the rocket, the propellers cannot become entangled with the drogue or its tether. When the quadcopter already is ejected from the rocket, we must ensure that the appendages, so the propeller arms and the landing gear, autonomously lock into place and continue that way as it lands. And NASA also has a safety requirement that requires a maximum kinetic energy of 75 foot-pound force at landing. And so since our estimated payload weight is 3.7 and with a parachute diameter of 3 feet, our estimated kinetic energy is 26.7 pounds. If we would need to make a heavier quadcopter or have the need to optimize our design, we would be able to increase its weight to 6.1 pounds and still meet NASA's safety requirement.
Since we will be working under NASA and working with high-power rocketry, there are several safety standards and regulations we must comply with. Some of the standards include National Association of Rocketry High-Power Safety Code, as well as the Federal Aviation Administration Code for Federal Regulations Part 101 and 107, and others such as these. Space exploration is an international effort, and since NASA is involved in the ISECG Space Corps with 13 other space agencies, as well as the ISS with 5 major space agencies, specifications will be available for our project both in metric and imperial units, and documentation such as pre-flight checklists will be available in a variety of languages. For our future work, we will perform simulations based on stress analysis as well as factor safety analysis. Manufacturing and assembly will begin in December up until February. That's what we're estimated to perform. For our thrust testing, even though we will be getting thrust data, we will be performing our own thrust analysis with a variety of different propellers. Stabilization programming, calibration, and autonomous action programming, which includes stabilized flight and as well as descent and arm and leg extension, will also be performed once we begin manufacturing in order to have that well done. For our projected timeline, We will complete our tasks. We're given these time ranges up until the competition in April. Thank you very much for your attention.
Are you concerned that your wires are going to get damaged during deploy?
That is currently a concern that we have to look into.
Okay. Do you have any redundant systems in your landing design?
Well, we have a parachute, we have a backup parachute to at least limit impact. As far as the legs extending, if the legs don't extend, we don't have any other way of
Having an upright landing.
achieving the upright landing. Perhaps if there's no crosswind at all.
Okay.
That's not the case.
Yeah, it would be, I think, nice to see some sort of redundant systems. So usually, if your primary, it looks like your primary mission in this case is to land the rocket upright, and if you have one fault in your system, you would fail because you have one fault. It's not a very robust design, so usually you have like two strings of whatever form of ejection you're using. So like if you're using like pyro to eject, you know, it will usually eject unless the line is like damaged, and in which case, you know, your secondary line will activate and you eject your legs. And then with your motors, like you could have, you know, two lines of power input, so that if for some reason one line is damaged, or you know, you crimped the wire incorrectly, or you nicked the you know, cable jack or something, and that damaged your wire, you don't lose functionality, right? Because you can't afford engine out, right, on your landing system, and you definitely don't want your electronic system to be the reason why you fail, because that would be just sad. It would be a cool explosion, yeah. Sad. So I would look into redundancy, and if you have margin, I would definitely consider adding redundant systems to your vehicle, and considering that that's standard practice across aerospace, it would be good for you guys to analyze how your systems can fail and what failures you can take before your system fails catastrophically. Because that's a thing that happens every day at SpaceX with that issue going on. So,
All right.
So after you eject your payload, you're using both parachutes and the quadcopter to provide you the upward motion to land. Is there a reason why you have both?
Parachute is mandated by NASA to make sure that we don't have an impact above 75 foot-pounds. They absolutely require that. We expect the quadcopter to mostly provide stabilization.
are you concerned with snagging on the tethers of your parachute? Because you're not going to go straight up and then deploy parachutes and then go down, right? Your parachute, your vehicle will either turn around and you deploy, and then if the tether is on the side of the rocket, you're not going to have a good time with your propellers.
Okay. The plan is for the parachute to deploy, the arms to extend, and the legs to extend at 3 different times. And our parachute deployment should take place well after ejection, so that we're clear of the rocket as well. So if it's descending, the parachute is open, there should be a problem with the arms extending and snagging on the parachute.
How are you going to time that though?
Using the altimeter. It's actually going to be based on the altimeter.
What if you pack your parachute wrong? Which is the thing that happens.
You have a redundant parachute.
Yeah, but now your timing is off. And now you're going to snag on your line. And you're going to go sideways because you can have 3 propellers thrusting and 1 is not doing anything. You need to have some sort of brake wire, I would think, that lets your system know that the parachute is successfully deployed, and then use that as like a safety check before you can engage your propellers. Because if not, I mean, the end result will still be that you will crash and explode. But at least this way you won't like probably like sway off into some scenario. It's something you don't want to hit.
Well, we'll have to see about programming the redundant parachute, but it also could be, having had a conference with some NASA people, that the redundant parachute might just be manual deployment. We do it from the ground. I mean, unfortunately, that might mean that the competition's over.
Yeah.
At that point, but
Design consideration, are you putting the redundant and your primary parachute on the same loop? Where you might have both deploy?
we'll make sure.